one-sided limits algebraically and asymptotes. So first, let's consider f of x is equal to the square root of x minus 2 plus 1. Now this is something that we've had to graph in like a pre-calculus class, and perfect for like the introduction of one-sided limits. So what I know is this x minus 2 is going to take that radical function, it's going to shift it right 2 and up 1. So it's going to go right 2, up 1. So we can see that our radical function is going to look like this. Now we can ask, what's the limit from the left and what's the limit from the right? So from the left, so left means from this negative side of our f of x. So our f of x is x minus 2 plus 1. And then I can also ask, what is the limit as x approaches 2 from the right-hand side, so from the positive direction of the square root of x minus 2 plus 1. Now, if I want to approach this limit from this direction, we can see that this function is not even defined over here. So I kind of tell my students, it's like having train tracks. If you have nowhere to ride, then the limit's not going to exist. So this does not exist. And you might see, does not exist, just saying D and E. As opposed to this one, if I want to approach from this right-hand side, is approaching 1. And the reason why is this function is defined for all of x values. No, its domain is going to go from 2 to infinity. That's the domain of this function. So this function is defined at x equals 2, which means I can just plug in x equals 2. So square root of 2 minus 2 plus 1, square root of 0 is 0 plus 1, which is going to be 1. And that's how you find that limit. Other one-sided limits we like to look at are piecewise functions. Equal to 2x plus 1 when x is less than 2, and x squared minus 4 when x is greater than or equal to 2. Now what we know is this function has two different curves depending on if you're to the negative side of 2 or if you're to the positive side of 2. So if we wanted to graph that, the graphing will help, but really the way we evaluate it's going to be algebraically. I just wanted to make sure that the graph makes sense to you. So, 2x plus 1 for all values less than 2. So I know it's going to have a y-intercept of 1. So it's going to cross there. And it's got a slope of 2. So up 2 over 1, up 2 over 1. We can see that open circle here because it doesn't equal 2. And it's going to look like this. So remember that this is y equals 2x plus 1 there. And then x squared minus 4. Well, you'd think that it'd have a y-intercept of negative 4, but this function is not defined at 0, so it'd have to be at 2. So if you plug in 2 squared is 4. So you can see that this function is going to be closed here because it's evaluated at 2. And so it's that quadratic. So this part right here is, y equals x squared minus 4. So the question is, how do I take the limit from the left and from the right-hand side of 2 again? So if I'm just going to call this f of x, so I don't have to write my piecewise function both times. So I'm taking the limit of this function here. So if I'm to the left of 2, remember the negative side of 2, I'm approaching it from this direction. And we can see that approaching from that direction is going to be on these tracks going this way. So it's looking like 1, 2, 3, 4, 5. So it's looking like this is going to be 5, its limit. So when I'm approaching on that, I know I'm going to use that particular function if I'm coming from the left. So this is going to be the limit as x approaches 2 from the negative side of 2x plus 1. That function, it's the entire curve, but it is defined at x equals 2, which means I can just plug in 2. So this is 2 times 2 plus 1. So that limit is 5, like we expected, it's 5. Now, if I want to approach from the positive direction, from the positive direction, you can see that I'd be on this curve. So as I'm approaching 2 from this direction, it looks like its y values is getting close to 0. So, when I'm choosing the limit of f of x, well, since these values are bigger than 2, I'm going to be using, this function now. So this is going to be the limit as x approaches 2 from the positive side. You can just say 2 now because you've defined a particular function. Now this function is defined at 2, which means I can plug in 2. So 2 squared minus 4, which is equal to 4 minus 4, which is 0. So that's its left-hand limit. Notice that this function doesn't have a limit at 2. It's got a left-hand limit and a right-hand limit at 2. But if I asked you what's the limit as x approaches 2 of f of x, we'd say it does not exist. Because for a limit to exist, the limit must exist from both directions, and the limit must be the same, and it's not. The y value of the left side is 5, and the y value from the right is 0. So that's why the actual limit doesn't exist. It just has limits from left and right. Vertical axis. Let's do asymptotes. F of x is equal to, let's say, the absolute value of x minus 3 all over x minus 3. So if I want to find the limit of this function of the absolute value of x minus 3 all over x minus 3, really this is a piecewise function that the absolute value is going to force this thing to be positive. So I'm just going to investigate what the absolute value looks like. So if I was just going to ask you y is equal to the absolute value of x minus 3, this is a piecewise function. So this is going to be negative x minus 3 when x is less than 3, and it's going to be equal to itself when x is greater than or equal to 3. Remember, if what's inside is negative, the absolute value is going to force it to be positive. So if this number is less than 3, say like 2 or 1 or 0 or anything between it and further, 2 minus 3 would be negative 1. The absolute value of negative 1 is positive 1. So when the values are less than 3, I have to change its sign. When the values are bigger than 3, then that means I can just leave it alone. So if this was like 4, 4 minus 3 is 1, and the absolute value is just going to be 1. So you don't have to do that sign change like you did above. So really, this is a piecewise function. This is minus x minus 3 all over x minus 3 all over x minus 3 over x minus 3. And this is when x is less than 3, and this is when x is greater than 3. Notice how I've excluded the equality here, because this function is not defined at 3. You can't plug in 3, so that's why I can't put an equal sign in there. Now, you can see that this is just negative 1 when x is less than 3, and this is positive 1 when x is greater than 3. So if I ask, let's say, what is the limit as x approaches 3 from the left-hand side of f of x? And if I ask what's the limit as x approaches 3 from the negative side of f of x, we can see they have two different values. If I'm approaching from the left-hand side, which means, below 3, we can see that this is going to be, negative 1. But if I'm approaching from the right-hand side, greater than 3, we can see it's going to be positive 1. Again, this thing doesn't have a limit at 3 because its left and right-hand limit are not the same. Vertical asymptote. To look at vertical asymptotes, we use a parent function of y, which is equal to 1 over x. We do it because it's a known function. And even though it has both horizontal and vertical asymptotes, we're really just looking at the vertical asymptote of, x is equal to 0. And we can see that it does this and then this. We'll get to its horizontal asymptotes in a little bit. So if I want to ask what's the limit as x approaches 0 from the left-hand side, so what's the limit as x approaches 0 from the left, so from the negative side of 1 over x, we can see that I'm on these train tracks going this way, and you can see that it's going down to negative infinity. So this is negative infinity. And if I ask what's the limit as x approaches 0 from the positive side of 1 over x, we can see that this is positive infinity, because I'm approaching from the positive side, so we're going to go up into here, which gives you positive infinity. Now that we have a base parent function for this, we want to be able to find limits of more general expressions, maybe something like, what about the limit? So evaluate. What is the limit as x approaches 2 from the negative side of 5 all over x minus 2? Well, this function is similar to this function. The 5 is going to stretch it vertically by 5, and the x minus 2 is going to shift it to the right 2. So really it's going to look just like this, except shifted right 2. So this has a vertical asymptote of 0. This is going to have a vertical asymptote of 2. So just shifting it to the right 2. Now, if we are approaching from the negative side, we can see that it's going to shoot down to negative infinity. So this is going to be equal to negative infinity. Another way you can look at it is just kind of keeping track of their signs. What's different about this limit compared to the other ones is in the introduction, or the algebraic limits, we had 0 over 0, but in this thing we don't. We actually have a constant over 0. So if the top is a constant and the bottom is 0, we're talking about a vertical asymptote, as opposed to a hole in the previous lesson. So keeping track of the signs, we can see that the top is going to be positive, and if I'm picking a number below 2, just like an easy number, let's say 1 is less than 2, 1 minus 2 is going to be a negative number. So this is going to be a positive over a negative, means negative infinity. If I want to take the limit as x approaches 2 from the positive side of 5 all over x minus 2, we can see this as positive infinity, because positive over a number bigger than 2, so a number bigger than 2 minus 2 is going to be positive as well. So positive over a positive, which gives us positive infinity. But again, it's just this function shifted right 2 for the most part. So what's interesting is we know that our vertical asymptotes because these are shooting off into plus or minus infinities. So let's say this is A, this is B, let's say C. What if I want to do the limit as x approaches 3 from the positive side of x plus 2 all over x minus 3? Well, we know that this is going to be a vertical asymptote, because if I plugged in 3, the top is going to be 5. It's a constant. It doesn't have to be 5 like that over there. It's a number that's not 0. And the bottom is going to be 0, so we're going to have a constant over 0. So I know that this is going to be some form of infinity. Now we just have to keep track of the signs. Well, the top is positive. Now this is a number bigger than 3, so just say 4. Make it easy. 4 minus 3 is a positive 1, so positive over a positive will give us positive infinity. And if I went from the negative direction, this is going to be negative infinity, because it would be a positive over a negative number. Horizontal asymptotes. We can still look at that 1 over x function. And we know that y equals 1 over x had a horizontal asymptote at 0. So when I ask for what's the limit as x approaches infinity, or even negative infinity of 1 over x, we know that this is equal to 0. Again, back to the graph looking like this and like this. And as I'm shooting to infinity, that the y value is getting close to this y is equal to 0. You can also think about what's a number divided by a very, very large number? Well, it's going to be 0.